All right, so we've heard a bit about auth in a few talks today. And I'm going to talk about a totally local first way of doing auth, a research project that we've been doing at Ink and Switch that is currently in alpha. There's code, it's open source, you can take a look at it, but maybe don't put it in production today. Okay. So, my name is Brooklyn Zelenka. You can find me in most places on the internet as Xpeed. And I was the project lead for Keyhive, and also worked on that with John Mumm and Alex Good. You'll be hearing from Alex directly after this talk about a related project. And there was a bunch of other teams in the design loop for this one too. And I was brought in mainly because I used to work on, or I guess I still work on, a project called UCAN that is a distributed auth protocol and to adapt that for Automerge. And we decided along the way to make it not work for more than just Automerge as well, so it's actually quite generic. And auth is one of these really scary things. I remember, 10, 12 years ago, working in just, web apps, and being really afraid that I was going to screw up the auth, and then you can't really undo that, right? And it's very complex, and all of your rules get really, intense. But unfortunately, or maybe fortunately, I have the personality type where I'm going to run into the burning building. And so I've done a bunch of these auth systems over the years and have tried to make it as simple as humanly possible. And good things, it turns out, come from Localfirst Conf. So this is last year, right after the conference. A bunch of us got together to talk about this problem and sort of collect the different approaches people had to it and the use cases and needs that they had. So here we are a year later. I mean, we only really got started on this project in about August, but about a year later, back at Localfirst Conf. So today we're going to talk about, or I'm going to talk about three things, and Alex is going to talk much more about one of them. That's capabilities, encryption, and trust minimized sync. Yesterday at the community day, a bunch of people were really excited about encryption. This is not a deep dive cryptography talk. We're going to talk about things at a very, very high level. Also, if you're really into capabilities, we're going to just touch on the surface of it. And then after this talk, you'll hear from Alex about trust minimized sync. And when you see his face on a slide, you'll know that's the thing you need to remember for his talk, because I get to cue him up for a bunch of things. So, motivation. Basically, the way I've been describing this to people is, what if Signal, the messaging app, it's end-to-end encrypted, worked for everything else, things that aren't just messaging? We want Localfirst, in general, but also especially auth, to be familiar to people. We don't want people to have to learn a huge new concept and stack of things and DSLs and all of these, right? It needs to work at live collaboration speed, work with interchangeable sync servers, right? So it's not just that you're always going through the one sync server all the time. You should be able to swap between them as they go up and down, or the person who's running it gets tired of running it. All of these things, you should be able to just move it automatically, which introduces new questions about how much do you trust a particular random interchangeable sync server. And we'll get to that a little bit more. And auth should be automatic. There's a version of auth that is just essentially git pull, where you decide, you look at it manually and say, yes, I want to accept that, no, I don't want to accept that. We want this to be automatic. Scale really changes things. And when you have something that's meant to be a generic protocol, you need to set an upper bound on what it can do. So it's very different if you're trying to do, 1 billion users in a single, shared space versus a smaller number. And so we set ourselves the goal of 100,000 of interlinked docs, tens of thousands of readers, thousands of writers, and hundreds of admins, sort of as an upper limit. And you can't talk about auth and security without talking about your paranoia level. And this is an extremely informal threat model that says basically secure against the FBI, but not against state actors like the NSA. So we're not trying to guard against things like they're collecting metadata about who you're sending, which IP addresses you're sending messages to, right? There are techniques for that. You can attack them on. We're just not going to handle those here. It's more what are, if somebody was really trying to get into your documents. How can we prevent them from doing that? As opposed to, maybe they have a quantum computer. We don't know, right? And of course, turns out, boring is good, actually. So we have some very cool pieces down in the stack, but it must be able to support things that look just like every other app. So if you go into Google Docs, there's a little button in the corner that says share. You click share, you get a list of who's in the doc and a way to invite them and what they can do, just right there. So if we do our job well, you can still drop down to the lower level APIs, but it should seem boring in a good way. It's also important before we dive in to talk about what Keyhive is not. People hear auth and they think identity. So Keyhive is describes what a user is authorized to do. We don't directly handle key management. We end up doing that, say, in the browser, for example, with the Web Crypto API. But that's not part of Keyhive itself directly. It's not identity. Identity is the mapping of a human being to some authorized agent. So we don't say, this is so-and-so, right? All that we're handling are the keys. And it's not a name system. You can there's so many name systems. Maybe you want to plug in the blue sky usernames, all of these. We have essentially a standard boundary where then you can plug into all of these other systems. I have a side project where I'm working on a totally Localfirst name system. That's not part of Keyhive. You should be able to plug in any name system that you want. So let's start with talking about how things work on the cloud today. We call this auth as place. So when you think about cloud auth, the picture most people have in their head is something like this. You have two users, they want to send messages to each other and nobody else, and it's going to go through some central server. And maybe you plug in OAuth or something like this just as as middleware, and it takes care of it for you. But that's hiding a lot of complexity under the hood. So it's really great that there's this mature tooling, but what's actually happening is quite a few more moving pieces. So we have the same two users, and we have our auth server. You present to the auth server, hey, here's who I am, some proof of who you are. And it says, yep, OK, great, here's usually a time-limited token back that you then go to the resource server and say, hey, I want to do this right, here's my token. It then turns around and talks to the auth server and says, hey, is this token still good? The auth server says, yep, yeah, that one's totally fine, great, here's your HTTP 200 back. Now you have a user who wants to read that. She goes through the same flow, presents her ID, gets back a token, and says, hey, I would like to read this. I'm going to do HTTP GET, and we send that. It checks back with the auth server and goes back again. So you'll notice that the auth server is in every step of this flow, right? It's on the hot path for every single request. This is really important because if one of these users turns out to be malicious, we want to be able to revoke that token so that they can't access it anymore. This is, in some ways, really convenient. We all understand how this kind of a thing would work and why we'd want to do these things, but comes with some serious downsides. The thing that has actually all of the power is the auth server. It can decide who's allowed to do what. If it goes down, you have no way of checking these tokens anymore. You can confuse it. Somebody could hack into it, change how it behaves. And the rules in them tend to get really complex over time because you keep adding special cases and they want another rule. But this is kind of like a sub-rule, and it kind of works slightly like this. So conceptually, over time, they become harder and harder to maintain. And it depends on the fact that you're across a network boundary. I can't read your entire database because I don't have physical access to the entire database. So we have a concept of over here and over there, and on the hot path every time is this connection. This is also a bottleneck for performance, and there's many, many papers written by Google and others on how to scale this picture. So obviously, we're in Localfirst. We want to be able to work even when there isn't an online server, auth server somewhere. And we basically want the picture to look something like this, right? We're going to have a bunch of concurrent writes, and people are offline and online, all of that stuff. But we want to think about it as if there was a history, and there's ranges of time when different users are allowed to write or read and not. And they can come and go and add more people and remove people over time. So that's kind of like conceptually what we're trying to do. In Localfirst, we have a different mechanism called auth as data. Essentially, your auth has to move around with your data wherever it lives, because we don't have that network boundary. So if I have it locally, and just to use one example that I think is more intuitive, you have encryption. Well, if you don't have the decryption key, you can't read it, no matter where it sits, right? And so that encryption travels around with the data because it's an encrypted blob. So we no longer have these ideas of auth here and data there. We just have auth and data. Usually, coming from if you've built full stack web apps, this kind of thing, usually the picture looks something like this. You have a data layer at the bottom, it's a database. Above that, you have compute, let's call it node. And above that, you have some plugin to do auth. Your single source of truth is your database. Compute mutates that, and often you'll just put all of your rules and all of the configuration for your auth layer in your data and have the compute layer actually manage that for you. But when we move things over into Localfirst, these two layers stay in the same order, but auth has to live at the bottom because it has to, again, the auth has to travel with the data. If it's encrypted, it has to be encrypted before it gets to you. Right? And before you send it back out to somebody else on the network, you have to encrypt it there too. So you actually have to build in auth from the bottom. So securing data wherever it happens to be, let's start with end-to-end encryption. There are many, many trade-offs when trying to encrypt Localfirst data. But here we have a graph of changes, and we need to decide what to encrypt. Do I encrypt the whole thing, parts of it? So if we encrypt each change individually, so in Automerge, this might be every keystroke, right? Because I am in a live collaboration. So I press A, I encrypt that, I send it across. This absolutely works, but it makes compression impossible. Once something's encrypted, it looks the same as noise. It's completely random. So we don't want to lose compression. That's how Automerge stays so light, right? So instead, what if we want really great compression? Well, we can take the entire graph and compress that and then encrypt that part. But not everybody has the entire graph, right? So some people have this chunk, others have that. And even if you have the entire thing, maybe you want to slice it up in different ways. And there's no clear way of doing this that's consistent unless you know what everybody else has, which you don't in Localfirst. So this is very, very important to the sync layer that Alex is going to be talking about next. Really what you want is something like my old writes, so the stuff at the bottom, I want those to be in big, nicely compressed chunks because those are unlikely to change. And then I want it to get more and more granular until we get to live collaboration where I'm sharing every individual keystroke. So we can do that sort of chunking, but we now need a way of chunking consistently across all of the participants without coordinating them, because we all might be offline from each other. So I want to be able to chunk this and compress without asking you, hey, how are you chunking it too? Luckily, every op either comes with a hash or you can hash it. And we can pick a hash hardness metric, like how many zeros are at the end of the hash, and that lets us just to probabilistically determine how big of a range that is, because if it's 2 zeros, maybe it's 100 on average will end up in that region. So in this case, we have some that end in 2 zeros. We can break up the graph like this. And just cleaning up for complexity here, we include the key for each predecessor in the graph. So all of its ancestors, its history, like so. Then we take that entire thing, including the key, we compress that all together and encrypt it. So now I have 3 encrypted chunks, whether or not you've already have part of them, we can now sync, well, I have the old history, but not the new history. Well, I only have to grab the new history, even though it's encrypted. The server can't read the content. at all. But we have these sort of chunks that are still, you can identify them by hash. Now we need a way of transferring to somebody else and getting back in. We are going to handwave massively over where this key comes from. If you're interested in how group key agreement happens, we have an entire article about it at that QR code. So you're able to drive this key. That lets you into the top of the graph, which then you can discover this key, which lets you into this middle chunk. You can discover that key, which lets you into this one. So by only having to drive a single key, we can get into the entire history. And then it's all decompressed and unencrypted again, and we're back to regular, normal CRDT land. Unfortunately, encryption is not enough because, like, yes, technically keys can get broken, but it's much more likely that you're going to invite the editor of the Atlantic into your group chat. Or post a key to, GitHub or Blue Sky or somewhere, right? So in addition to encryption, you also have to keep the encrypted bytes as much as you can, or do best effort, out of the hands of other people that might want to break in. I sometimes call this the if you know principle, right? Once it's decrypted and somebody has a copy of it, they have a copy of it. In the security literature, people often talk about the surprise birthday party that you're planning. If somebody knows that you're planning a surprise birthday party, you can't make them forget that. So having a defense in-depth strategy is your only option here. So we encrypt bytes so that the sync server can't read your data. We only transfer it to people that are authorized. We'll talk about that in a moment. And if somebody breaks into the sync server, hey, it's still encrypted. So it's defense in depth. So how do we determine who's allowed to get the bytes or to do writes? So we have a few different levels of ability in the membership graph. The first is pull. This is, I'm allowed to retrieve bytes from somebody else, another member of the network, over HTTP, Bluetooth, SneakerNet, doesn't really matter. I'm allowed to actually request that. This is the stuff that Alex is going to be talking about. Level above that, you're added to the group that can do this key derivation step. A level above that, you're allowed to do writes, and we'll show you how to do the writes in a second, but it's all the same mechanism. And one above that is admin, who can kick anybody out of the group as needed. We think that this is sufficiently powerful for most applications, and we'll talk about how to add on top of this a topology for your authorization too. So instead of having this picture that we talked about earlier, Cloud Auth, we use a model called capabilities, which are extremely powerful, and you can use them to model role-based access control lists, all of these other models too. Plus, they are totally distributed and self-certifying. So they are cryptographically secure. So we start with a user who wants to access a document. Everything in the system has a key pair, or at least a public key. The document itself is also identified by public key. When it's created, it also has a private key, and it signs a certificate or a permission to this user saying, yep, they're allowed to do whatever one of those levels was, maybe write the document. And it includes from the document to the user's public key, and then signs it. And then that user can turn around and say, hey, I want to invite somebody else to this document. And from his public key to this, I guess, mechanics public key, right? So we have this chain of certificates. And then when you want to actually go and do something with the document, you create what's called an invocation. So when you do that update, it includes references to this entire chain. So we close the loop. So we have a signature chain that goes all the way back to that document that originated it. So we can now check, regardless who has it, no matter where it is, at any time, yes, this at some point was authorized. Because everything is identified by public keys, we can also now link together documents, which is to say, if you want to build a file system, you say if you have access to this directory, you have access to that directory, you have access to this file. As a high-level API, and we also expose lower-level APIs too, but high-level API, this is sort of your standard Automerge style API, where you have a document handle, and then you call change on it, and then you can make some changes. And we add a few more. One is add member, and the role that they have. Another is remove member. And that's it. That's the entire API you need. We never move keys around. So yesterday at the community day, some people were asking, like, OK, so each document has a key. How do I get that key? It never moves. You only use those certificates. And to model things like users or teams or groups, it's all the same mechanism. So we have one key per device or browsing context or whatever. So for example, in this case, we'll have one key for Alice's phone and another for Alice's laptop. And we have a group, which is Alice. It's basically a document without content in it. It can delegate to others and receive delegations from other nodes in this graph. And this Alice group delegates admin authority to these devices. And then if we have some documents like this LaTeX paper and some meeting notes, maybe we create another group called Ink and Switch. And these have different, again, permissions. So you can do read, another you can do writes. And Ink and Switch says, you know what, we really trust Alice. Alice can do administrative things as a maximum for everything that we can do. And you can add more people to that group. In the same way that you can add devices, you can add more users to that group. So there isn't a distinction between users, devices, groups, documents. At this layer, it's just IDs. You can also bring in multiple sources into them, right? So this could be another group that's all of your kids' homework. And then you can delegate these down to specific contexts like apps, right? And you can even scope them down to not everything I can do, but only this one, only things from this one source. And then we watch from a flow of authority. I can access this LaTeX paper. That gave me write access. From Ink and Switch to Alice, that's admin. But the smallest of the two is write. So anyone in Ink and Switch can write, so Alice can write. Which means that Alice's laptop can write, which means that the LaTeX editor can write to it. And so we encode, instead of as rules, we encode it as just a graph of how the authority flows through the system. And this is sufficiently powerful to model, again, access control lists and things like that. If you have this graph, so this, we're talking about this as certificates, but you're collecting all of these certificates all the time, and you're distributing them as a CRDT. So they actually form a membership CRDT. And so if you're looking at your graph of documents, you can say, OK, who has access to this doc? Because I've got a request in to replicate with a bunch of other people. Well, I can run the graph forward and say, oh, OK, the leaves are all of these people, or all of these devices. They all have access to it. And this is how we get our little list in the share menu of who can do what. And if I'm a user, I can say, well, which documents am I allowed to touch? And we run it backwards, and we do the same thing. We're like, OK, I can touch these documents. Great. So we touched on sort of a very, very high level of this. Mutation control, roles, membership graph, read control with end-to-end encryption and causal encryption. We didn't talk about how we do key sharing and deriving that magic key that lets you in once you've synced these encrypted blobs around, or revocation, how to remove access to somebody, and especially what happens when multiple admins remove each other. It's actually a tricky case, but you can find out more about those things at that QR code. We've done a bunch of writing about this. Thanks.